And first of all, we have got Seiryo Sugiura from the University of Tokyo, so I'll hand over.
Thank you very much. It's my pleasure to introduce our approach for cardiotoxicity testing. In the beginning, I will introduce briefly about our model. Then I will talk about the in silico screening system using this model. And finally, I will show the multidimensional hazard map and touch upon the uncertainty visualized in the previous speakers of the meeting told us that the complex model introduced higher order of uncertainty. I completely agree, but nevertheless, we prefer to use heart model rather than cell model, just because we wanted to see whether the drug-induced actually induce arrhythmia instead of looking at these, surrogate biomarkers. Our model is based on the finite element method, the morphology of which was taken from the multi-slice CT scan data, and to the model we implemented cell model of cell model of electrophysiology coupled with cross-bridge dynamics. Although it is not used for the current analysis, we have a capability to model the blood inside the chamber and solve the fluid structure interaction analysis by strong coupling method. We also created torso for the analysis of electrocardiogram. We used these models of These models of electrophysiology. For the ventricle, we adopted the O'Hara model, consisting of 3 species of cells having different action potential durations. These models are arranged transmurally in this manner. It looks like discrete fashion, but because of the electrical coupling, the resultant distribution of action potential is smoothed out like this. We also introduced apico-basal, which is longitudinal gradient of action potential, both of which are essential to reproduce physiological shape of T waves. After all these setup, we injected some current into the pacemaker site. Then the activation propagates to adjacent cell one by one, and when it reaches the ventricle through the conduction system, and finally activate the working myocardium. Now, in the activated cells, calcium concentration goes up to trigger the cross-bridge dynamics to generate force. Heart stops. I'm sorry. And the ventricular wall squeeze the blood inside to generate pressure and flow. When we put this heart model into the torso and calculate the bidomain equations in the heart domain and the Laplace equation outside the heart domain, we can obtain body surface potential map by placing a pair of electrodes like this and take the difference. We can observe electrocardiogram like this. This is the second limb lead, and in a similar way, we can have 12 lead electrocardiogram. Using this model, we developed the in silico screening system for the drug-induced arrhythmia. In the following study, only the electrophysiology of ventricles was solved just because saving the computational burden. This is a kind of hybrid system, so that our collaborators in academia and pharmaceutical companies measure the inhibitory action of the compound on 6 ion channels to provide us this kind of concentration inhibition relationships. Based on these data, we could reproduce the state of function of the cell and the specific concentration of the drug, and also the function of the ventricle composed of those cells to obtain electrocardiogram. We selected 12 benchmark drugs having reported to have different arrhythmogenic risk. This is from Redfan's paper. This slide shows the kind of pharmacological spectra of test drugs. In each panel, the green dots represent the effective therapeutic plasma concentrations. We analyzed these 6 channels. This slide compares the 2 drugs. This one is antipeptic, already withdrawn from the market due to the arrhythmic event. This one is a calcium blocker with virtually no report of arrhythmic event, despite the long history of clinical use. Starting from the control condition without any drug, we applied ETP therapeutic concentrations. No appreciable change in ECG was observed. We further increased the dose to 10 times ETPC. So you have noticed that for both drugs, QT interval prolonged significantly. At 30 times ETPC, we observed arrhythmia, polymorphic VT for cisapride, this one. But although the QT interval prolonged furthermore, but the arrhythmia is still regular with verapamil. Even more, 50 times ETPC, although that QRS waves deformed and QT interval prolonged tremendously, but still the rhythm is regular. This slide summarizes the result of 12 test drugs. Drugs are ranged from the ones with high risk to safe drug according to the Redfan's criteria. For those in drugs in categories 1 to 3, those we consider those risk drugs. I'm sorry. The bar graph indicates the threshold concentration at which we observed arrhythmias. We analyzed at 3 different heart rates, but no appreciable change were identified. But for the drugs in categories 4 and 5, we never observed arrhythmias. That means this screening system provides no false positive results. This slide compares the performance of the screening system with other methods. As you see that for QT interval and HARC may produce false positive results. Because, I'm sorry, those drugs similarly arranged from risk drugs to safe drugs. 1 to 3 are risk drugs we considered. 4 and 5 are safe drugs. mice method is fairly good because this one can discriminate risk drugs from safe drugs, but we would like to say that the difference maybe is fairly small. But it is clear our method can discriminate risk drugs from safe drugs. After completing this project, we came up with an idea that drug effects can be characterized by a trajectory in a multi-dimensional space, the coordinate of which represents each inhibition of each current. And hopefully we can identify the region at risk somewhere in the space, and maybe the distance between the risk region and this trajectory can be considered as a safety margin of the drug. But anyway, we have to repeat computationally expensive simulations for each new drugs. However, if the data points in the space has been filled beforehand, we don't need to repeat the simulation. Just based on the pharmacological data, connecting the existing data points, then we can have a drug effect trajectory representing a drug effect in the space and assess the risk. So that is our motivation to create a hazard map for drug-induced arrhythmias. We sampled those data points. You may say that data points are so sparsely distributed in the space, but the total number of combinations of 5 ion channels was more than 9,000. And based on these numbers, we estimated that the total computational cost required for nearly 10,000 patents would be 70 million core hours. At that time, we are lucky enough to have a chance to share certain amount of machine time with a supercomputer. So we performed kind of embarrassingly parallel computing to fill the entire space. But after the computation is over, we found that how to visualize the data. Visualization of 5-dimensional space on the 2-dimensional plane like this would be it's very hard. So what we did was subdivide that entire space to three-dimensional subspace, and arrange them as the remaining 2 ion currents as the parameters. In each space is in subspace is made up of IKL coordinates, sodium coordinates, and calcium coordinates. In each space, region at risk is shown as a dark area, and the QT interval is shown by color. For instance, if we want to analyze this drug up to this concentration, because the IKS and sodium inhibition is virtually nothing, so we can only use this subspace. This is an example. Starting from the control condition without any inhibitions, we obtain these ECG. We increase the concentration to 4 times ETPC. Then you see that QT interval prolonged. And at 7.9 times, we observed arrhythmias. This is another example with quinidine. This is interesting because the trajectory hits the regional risk at a relatively low concentration. But when we increased it, it comes out to the safe region. This finding is maybe concordant with the clinical observation that accident with quinidine is reported to occur at relatively low concentrations. We tested performance of our system by comparing those 3 risk categories. The red rectangles indicate that results disagree with the prediction. But overall, we think our system produces acceptable performance. As I told you, a multi-scale model has multiple origin of uncertainty. At every levels, we have very many unknowns and uncertainties. I will show the impact of those errors and the variations. Some of them. First, one is uncertainty originated from the experimental error. In our analysis, the pharmacological property is characterized by 2 parameters, namely IC50 and Hill coefficient. Those are obtained by fitting this curve to very limited number of data points, so quite naturally we can expect variation of results. For instance, when we increased these parameters, we can have we observe a shift of concentration inhibition relationships. It's very minimal, but with the 20% change produces very minimal shift of the curve. So similarly, we observe the shift of trajectory in a subspace. But in the case of drug with very small safety margins, only small changes in estimation of those parameters introduce misleading results. For instance, with average data, this one, quinidine, was judged as a risk drug, but the estimation of the IC50 was different, only by 20%. We may judge it safe drug. Similarly, about the Hill coefficient, we saw the same thing. Only a tiny variation is those parameters produces a misleading result. Another example of variation uncertainty is genetic one. It's not a drug side, it's subject individual side. For instance, single nucleotide polymorphism of the IKS channel. This one is fairly common among Japanese population and causes 30% reduction of the current density. But only 30% of reduction of the IKS current reduction produces only a minor change in the QT interval. So the phenotype is mild and manifests only under pathological conditions like hypokalemia, bradycardia, and so forth. Those changes can be visualized in our hazard map by just reducing the IKS current. In order to do that, we need to use different subspaces, switch from this one to this one. The difference is the region of risk region expanded a little, so that the threshold for arrhythmia decreased a little bit in the case of Beperdu. But in the case of ranolazine, 30% reduction of the IKS current make this safe drug to a risk drug at fairly low concentration. I know that there are many unknowns in a complex system. One is the I'm sorry. Oops. One is how that those three species of cell as arranged transmullarly, and another is pathological conditions and size of the heart main matters. Those factors cannot be included in our hazard map. In summary, the estimation of the pharmacological parameters shifts the trajectory in a space, and individual variations change the region at risk in the hazard map. This hazard map is accessible freely at our website, so that you can interactively assess your drug just based on the IC50 and Hill coefficient. And numerical data of the ECG are available at the Figshare website too. Maybe 2 minutes. Finally, you may have noticed that in my presentation, arrhythmia takes place spontaneously, but in the real world, it requires some triggers. So I will give extra stimulus under sinus conditions and see what happens. Please follow the activation pattern and ECG and left ventricular pressures. Starting from the sinus rhythm, I apply the extra stimulus. Then we see ventricular tachycardia. It reverts to sinus rhythm once again, but then the rhythm went to VTAC, and it degenerates to torsade. And finally, BF, the pressures goes down. Thank you very much.
Any questions?
It looked like the QT interval prolongs up to 300 milliseconds before you get to arrhythmic behaviour. Do you call it safe?
With which drug?
Well, with any of the red region looked like 300 milliseconds before you get to the arrhythmia. Is that right?
I didn't notice that, but looks like it's a kind of acceptable range. Some drug introduce tremendous prolongation.
I'm just wondering about the kind of a bit of a safety margin in QT prolongation.
I will look at it. Thank you.
Thank you for the talk. I was wondering, you don't take into account the atrium and the AV node, and maybe that might explain why you did not get any arrhythmia hazard for verapamil, because verapamil is doing a lot of work on the sinoatrial node and the AV node, and you might get into trouble. And so you predict a hazard for ventricular arrhythmia, which is purely ventricular induced, but not in combination with the other parts of the heart. Or am I wrong?
But verapamil is categorized as class 5, which means no instance has been reported for ventricular arrhythmias. I agree with you that it affects AV conduction, but in terms
It's
of
just an example. You know, there are other, verapamil, for example, is not indicated if you are very young, and if you have a risk of having WPW, or if you have a contraction problem. So there is more to it than only, that's what I only want to say, there's more to it than only looking purely at the ventricles and having a fixed pacing rate, and then look whether you can induce a ventricular problem.
reentrant maybe induced, right.
Yeah. So very interesting results. I wanted to ask, your spontaneously arising arrhythmias, are they from triggered activity like EIDs and DIDs here? Or
Yes, when we look at closely, mainly initiated in the M cell, from the M cell.
and also, do you include any mechano-electrical feedback in your model?
No, not.
It means that in principle you can study initiation of arrhythmias without mechanics, yes? But mechanics of course helps you to predict output, but it can speed up, of course. Yeah. Thank you.
Okay. Well, let's thank Seiryo again.